Everyone, today we're doing 12b, which is further matrix equations. So pretty much what we're going to do is use everything that we've learnt so far and apply it to application problems. So one, apply matrix arithmetic to word problems, and also in particular solve simultaneous equations using matrices. The whole idea behind this is we've learnt how to subtract, add, scalar multiply, normal multiply, do all of that to be able to get a letter on its own or a matrix on its own when we're doing algebra. The one thing that we've learned last lesson is how to divide matrices if we need to get a matrix on its own. So that's exactly the concept that we're looking at today. So a matrix equation of the type AX equals B can be solved by multiplying both sides of the equation by A inverse. So I'll just show you exactly how it works in terms of the arithmetic of it. So if we've got AX is equal to B, now usually what we would do to get X by itself is we would divide both sides by A. But in matrices we can't divide, we can only take the inverse. So what we would do is take the inverse of A. And so because I have pre-multiplied by my inverse of A, I'm going to have to pre-multiply on the other side as well. So remember, whatever you do to one side, you must do to the other. Now remember that A inverse times the actual matrix A is just equal to the identity. So that itself there is the identity matrix. That's going to be IX is equal to A inverse B. And remember how the identity of X, or identity times any matrix, is just going to equal that matrix itself. So that'll be X equals A inverse B. So in your exam or your SAC, when you're asked to rearrange a formula to use a matrix, this is the kind of working out that will ensure that you score full marks so that your examiner knows exactly what you're going on about. If we look at the first dot point, that's exactly what we've just done then. And then just looking at the second dot point, it's the exact same idea except A is being post-multiplied. So what I have to do is take the inverse by post-multiplying it. So X will be equal to B times A inverse. So you just really need to be aware of where you multiply your inverse. Alright, so what we're going to do is just try a couple of examples of this whole idea. So for example 30, the matrix A is equal to that, find the determinant, and then find A inverse. So of course all of this can be done by calculator, but for the first example I'm just going to do it by hand, and I'm going to do it pretty quickly. So that's A, B, C, D, remembering that our determinant is equal to AD minus BC. It's a pretty weird A, but just ignore that. So that's 3 times 6 minus 1 times 2. 3 times 6 is 18. And 1 times 2 is 2, so 18 minus 2 is 16. That is my determinant. And then the A inverse, remember we do 1 over the determinant, so that's 1 over 16. Switching D and A, so that's 6 and 3, and then putting a negative in front of B and C. So that's negative 1. And that is your inverse there. Cool, so part C then says find X if AX is equal to this. So what we know is that, they've actually given us the formula just there. Given that AX is equal to B, then X is equal to A inverse B. Remember that you're pre-multiplying because A is on the outside. So X is then going to equal A inverse, so that's 1 over 16, 6, negative 2, negative 1, 3 times matrix B, and B is on the outside there. So they've called this matrix there B, 5, 6, 7, 2. And now all you have to do is go on with your multiplication. I'm going to multiply the determinant in at the end. So for now, we're just going to do our row by column idea. So row 1, column 1. So I've done multiplication quite a few times now, so I'm really just going to run through it as quickly as I possibly can. 6 times 5 minus 14. Row 1, column 2, that's going to be 36 minus 4. Row 2, column 1, that's going to be negative 1 times 5, so that's negative 5 plus 21. And row 2, column 2 is going to be negative 6 plus 6. So work that out. That's going to be 16, 32, 16, and 0. And don't forget that 1 on the 16 on outside. And I'll just do it up here because I run out of space. What you now need to do, I've got 1 over 16 on the outside, so this little thing here, 1 over 16, is the same as dividing by 16. So that's what it's saying. 1 over 16 is the same thing as dividing by 16. So all I have to do is just divide each of my numbers in this matrix by 16. So 16 divided by 16 is 1, 32 divided by 16 is 2, 16 divided by 16 is 1, and 0 divided by 16 is just 0. And there you go, that is what X is equal to. So, given an equation, work out what AX equals B is going to be, so work out what matrix is what, rearrange to get X by itself, and multiply it out. Of course, this can all be done on the calculator, which will be a lot quicker, but you should also know how to do it by hand, and I really encourage you to practice this by hand at first, because calculator is really easy, just to get your head around it and to understand how to do it. Okay, so example 31 in your book, you've got 4 scenarios there. This is going to be exactly the same as the example that we've done before. So I actually want you to try this, and in class we'll go through the answers. What I am going to do is I'm just going to talk through, only for part A and part B, how we would go about getting X by itself. So In this case, a is being pre-multiplied, which means to get x by itself, I need to take the inverse by pre-multiplying it to the other side. However, in part b, because a is being post-multiplied, for me to get x by itself, I need to post-multiply by the inverse, so that'll be b a inverse. Okay, see if you can work out what you've got to do for part C and D, work out for x what that's going to all equal, and we'll explore what that is in class. Alright, so applications. The key application for matrices using this whole concept of getting x by itself is your simultaneous equations. So what you want to be able to do is to have a look at simultaneous equations like this, be able to place them into a matrix and then to solve for it. So let's work through getting these equations into matrices. Now, my first matrix is going to represent my numbers. So these are going to be the coefficients of x and this is the coefficients of y. And they're each going to be multiplied by the letters of x and y. And that is going to equal my answer, whatever my answer is going to be. So the coefficient of x in equation 1 is 3, coefficient of y is negative 2, coefficient of x in equation 2 is 5, and the coefficient of y is negative 3. Now if you think about it, if we're doing the whole row by column thing as to how this works, have a look at this. I'm going to have 3 times x minus 2 times y. See, and that's going to give me my answer, which is going to be on the other side. So that's how that whole thing works in terms of putting our equations into matrices, and we've kind of looked at that previously in another exercise, so that's why I'm not going to go through it too much. But just in case you forgot, that's how you do it. So those are our equations placed into matrices. Now, if I call this one matrix A, this one matrix X, and this one matrix B, hopefully you can recognize the form that it's in now. I can rearrange to get x by itself. So ax is equal to b, which means x is going to equal to, remember we're pre-multiplying it, a inverse of b. And then you can just pretty much chuck that on your calculator. So xy is going to equal to this matrix here, 3, negative 2, 5, negative 3, to the power of negative 1. Don't forget that we need that inverse, multiplied by matrix 5 and 9. So let's put that on our calculator. And there you have it, that's your answer, 3 and 2. So that is equal to 3 and 2. That's what x and y equals to. And then what that means is that x is equal to 3, y is equal to 2, and that is the intersection point. So if I were to draw like a really, really rough linear sketch of what this might look like, these could be my two equations like this and like that. And then this point over here, where they intersect, that is going to be the point 3 and 2. So that's what that all means. And that's the whole point of this, and it's just a very quick way of finding the intersection point. Now, yes, you can just solve this equation and that equation, but this is the way that you do it using matrix methods. That's how you go about doing that, and then the exact same thing if you happen to have 3 equations with 3 unknowns. So what I'd like you to do is pause the video now, try to do this example by yourself, and then I'll quickly go through it. Alright, so exactly the same as we had before, we want to set up our 3 equations. So we've got a, x equals b. This time, a has x, y, and z. It's got 3 pronumerals, and so we'll have 3 coefficients for each equation. So it's going to be 1, 3, negative 1, 2, 1, 1, 1, negative 1, if I can write, and negative 2, times x, y, z, and that is going to equal 15, 7, and 0. And so what we want to do is pre-multiply both sides of the equation by a inverse, and so that'll just be this equation over here. So x equals a inverse times b, and we can chuck that into our calculator. This time we want a 3 by 3. And that'll be to the power of negative 1. Once again, don't forget that inverse. And we're multiplying it by a 3 by 1 this time. So 3 rows, 1 column. And there you have it. Those are our answers, 2, 4, and negative 1. So we will end up having x, y, z is equal to 2, 4, negative 1. And so what we can say is that x is equal to 2, y is equal to 4, and z is equal to negative 1. And once again, this literally means it is in a plane. So if I were to draw a 3D plane, so in this case, we've got x, y, and z. Now think of this as 3D. We've got 3 equations. I don't know how they're going to go, but say it's like that, that, and that. all three of them intersect at this particular point. And this particular point, this coordinate, is 2, 4, and -1. So that's kind of cool. If you haven't seen a 3D plane before, that's the way that you go about doing it, and what it means in real life. So obviously not an important bit of information, but maybe that'll make it a little bit more interesting for you. So one thing that you have to note is that not every single pair of simultaneous linear equations have a solution. We've had a look at this before when we did linear. There are two particular examples where there's no unique solution, as in there's no one solution. The first situation is this one over here. So if we have a plane and we've got this equation and that equation, do you remember what this is called? It's parallel lines. They never ever intersect. Okay, so parallel lines do not have a solution. Also, another time where it does not have a unique solution is when you've got a linear equation and then you've literally got the exact same equation that just lies over the top. And this is what we say that the lines coincide, or they are collinear. That's the proper term for them. And so in this case, there's no one solution, but in fact, every single point on this is a solution because it's just always intersecting. So what we would say is that there is no unique solution. The two key property about this is that this is when the determinant is equal to 0. So remember in the previous exercise how we talked about you can't find the inverse if the determinant is equal to 0. The reason for that is that because there is no one intersection point. And so we can see that physically with parallel lines and also collinear lines. So what you would have to do is first check that your determinant doesn't equal to 0, and then you can go ahead and find your solutions. Your calculator will tell you anyway if there are no solutions. But what we can do is we can test it out. I'm going to do example 34. I want you to do example 35 and we'll explore that one in class. So very quickly, let's get through this. We're going to write up our matrix, and that is times by matrix xy equals 5, 7. Now, let's just test to see whether there is going to be a solution or not. So we can test it using either the calculator or by hand. I'll do it by hand first. I'll show you how to do it on the calculator. So the determinant is equal to, remember, first let's label them, AD minus BC. So that's 3 times -4 minus B times C. So 6 times -2. So 3 times -4 is going to be -12. And then -6 plus -2 is going to be +12. And -12 plus 12 is actually equal to 0. So there's no point of even going on because this solution, it's undefined. So what you can say is the proper answer for it is that there are no unique solutions. To test the determinant on your calculator, because I haven't shown you that before, I'll quickly do it now. Alright, so to be able to find the determinant, you can either go to menu, matrix, vector, and 3, determinant, or you can just type in DET and it comes up as a function. Put in your matrix, if you remember what it is. 3, -2, 6, -4. And you'll see it comes up as 0. If I were to find the inverse of that matrix, but that's the power of -1. See how it says singular matrix, it doesn't work, which means that the determinant is 0, there is no inverse that exists. Alrighty, so try example 35, we'll go through that one in class, and that's it. That's how you use matrices to apply matrix arithmetic to word problems and also how to solve simultaneous equations using matrices. So I hope that was all pretty easy. Just give this exercise every question a shot. It's really, really important. Very common exam questions. So yeah, good luck.